Now return to Warplane. Air Force to Air Power follows the key advances that defined World War II and transformed military aviation. Coming up on Warplane, World War II transforms air power.
We see the blending of the electronic revolution with traditional aeronautics.
Radar reshapes air defenses.
The Army and the Navy embraced radar with a vengeance.
And strategic bombing brings new waves of destruction.
We are going over at low level with incendiaries, and we're going to burn those cities to the ground.
Conflict drives technology on Warplane.
The airplane was created in peace, but shaped by war. From its earliest beginnings, military commanders recognized the potential of the weapon in the sky and used it to dramatic effect. As World War I ground itself into the mud of Europe, only the planes were free to move. First as scouts, informing on enemy positions. Then as spotters, guiding their own big guns to the targets. Fighters evolved next, then bombers. But as the military importance of the warplane grew, so did demands on its performance. In the years between the two world wars, planes got faster and more powerful. Aerodynamic engineering was born. And increasingly sophisticated communications led to both better offense and defense. The shift was gradual but momentous. And with it came the true beginning of military air power. Today's cutting-edge warplane has been shaped by time and experience. 100 years of research has produced a craft so sleek it can slice through the skies without detection. And what we can see only scratches the surface. Beneath the skin of this U.S. Air Force F-22 Raptor lie all the assets of a 21st century warrior. The Raptor's teeth are just well hidden. This was not the case with the first generation of warplanes. During the Great War, everything was on the outside except the pilot. But as the war came to an end, a new scientific discipline was brewing that would change the very fundamentals of airplane design. It came from an unlikely source.
The Germans, the nation that's just lost World War I, is the nation that's pointing the way to the future.
But the work had begun before the end of the war, far from the front. Here, deep in central Germany at the University of Göttingen, pioneering research scientist Ludwig Prandtl and his colleagues were exploring the science of staying aloft.
Physicists, fluid dynamicists, look at these new machines and say, if we understood what was happening here at a fundamental level, we could improve design and performance and efficiency and all of those things.
Prandtl was inventing the science of aerodynamics and learning how to get the most lift out of an aircraft's wing. His discoveries were applied to the Fokker D7, a plane that did not have to fly fast to stay aloft. In fact, it could fly slower than any other plane, eluding enemy aircraft not by outrunning them, but by outflying them. Intrigued, the Allies demanded the surrender of an intact D7 at the end of the war.
Yeah, might as well just grab it. Well, yeah, we'll just let it on the ground and we'll grab it and
At the Kirsten Wind Tunnel in Seattle, Washington, a model reveals just what was so special about the Fokker D7. Its ability to stay aloft came from a counterintuitive wing design developed by Prandtl and his team.
Is everything online?
Yep.
During the First World War, the Germans were actually doing a lot of research in their universities that showed them that some of the data that they had before was wrong.
All right, ready for wind?
Ready for wind?
There it goes.
The scaling issues in the wind tunnel test that they'd done earlier indicated that they wanted to have thin wings because they believed that's what you needed to be aerodynamically efficient.
Take it up nice and slow.
The original thinking was that a thin wing would create less drag.
What's the lift limit set to?
0.7.
Look at a boat in the water, you've got this huge wake. Well, the airplane is creating a wake also. The smaller the wake, the less drag you have. The bigger the wake, the bigger drag you have.
You can see where it's kind of separating right before the trailing edge.
It's looking pretty good.
The Germans discovered that a fat airfoil will have no more drag than a thin airfoil.
Start complete. Series is complete.
This was useful because the fatter wing had some unique advantages. The thicker the front edge, the more gradual the transition between having lift and not having lift. This gave the pilots more warning of an approaching stall. The thick wing had other benefits as well.
Crandall's wing, with the much thicker cross-section, meant you could put a strut inside the wing, a cantilever, and remove a lot of the external bracing. Greatly reduces drag. And this would also, in fact, pave the way to the great leap forward in airframe technology, which would come between the wars, namely the monoplane.
The transition to the monoplane took flight to a whole new level. With the elimination of the second wing and all the straps and struts that went with it, the aircraft instantly became more aerodynamic. And putting the fuel tanks, wheels, and guns inside the remaining wing made it even more efficient. The change was universal and permanent. The thick-winged monoplane would allow man to do far more in the sky than anyone had ever expected. But in the 1920s, with the world at peace, it was not great nations' militaries that would immediately reap the benefits. The first action the new monoplane saw came at highly publicized worldwide races for the coveted Schneider Trophy, the holy grail of air racing. These planes were the NASCAR speedsters of their day.
The Schneider Trophy during the 1920s and the early 30s pushed aerodynamics, propulsion, streamlining especially, to get the airplanes to fly faster.
It was at international competitions like these that the warplanes of the future were being forged. Italy, America, and France all took turns at the top, sometimes doubling the speed record from the previous year. Even without a war to drive it, technology was progressing rapidly.
By the end of the First World War, aircraft speeds might have been at a maximum 140 miles an hour. By the early 30s, speeds had trebled.
According to the rules of the competition, the first nation to win 3 races within a 5-year span would get to keep the Schneider Trophy forever. It happened in 1931, when a brilliant young British designer named R.J. Mitchell won 3 races in succession with his Supermarine racer. Mitchell, chief aircraft designer for the Supermarine Company, was building civilian racers because in a time of grave recession and no looming threat of war, the British government was not putting much money into aviation. But his prowess with the racers was not overlooked. And within 5 years, he had built on his civilian success and created one of the greatest fighter planes of all time, the legendary Mark I Spitfire.
We looked at this thing, we walked around it, we stroked it, we sat in it. I fell in love with it. It was the most beautiful thing I had ever seen.
The Spitfire, in many respects, is one of the most successful designs ever. The Spitfire was more aerodynamically refined. It had an elliptical wing, which gives you perhaps 2 to 3% more lift per unit of drag.
The elliptical wing was no accident. Mitchell had actually hired an aerodynamicist specifically to design it. The wing was, and still is, one of the most efficient ever built.
You didn't climb into Spitfire to fly. You put wings on your own back and flew. It's the only airplane I've ever flown that's been like that.
And it could do a lot more than just fly. Housing 8 30 caliber machine guns and later 4 20mm cannons, the Spitfire was well named. A piece of technology ahead of its time. It was ready for war. It wouldn't have long to wait. In 1939, the ferocity of Hitler's attack caught Europe unprepared. The sheer speed of the Nazi advance, undertaken with a lethal combination of air and land forces, left country after country in disarray. This World War looked nothing like the last.
World War II is really the technology war. It's really quite a race, and the side that's going to win this race is really going to win the war.
By combining and coordinating his forces, Adolf Hitler had created a complete battle system. Using radios, his warplanes, tanks, and infantry divisions were in constant communication. His commanders worked together to roll out a fast-moving wave of terror. The system was called Blitzkrieg, the Lightning War.
Making the system work is key. And that's what you see in World War II, the development of these great technological systems.
Hitler's unstoppable forces racked up victory after victory until all that stood between them and the total conquest of Europe was a strip of water a little over 20 miles wide. On the other side lay England. The Nazi warplanes didn't take long to breach the channel and continue their aggressive advance. But the British were expecting them and had been preparing for just such an assault. For decades, they had been quietly building an invisible wall of defense to guard their island nation from aerial attacks. The result was a wall of protection 5 miles high and 600 miles long. It was a system that had been in the works since the very first airplane crossed the English Channel in 1909.
Britain, even during the First World War, had developed the nucleus of a fighter defense system. They had developed a system of ground spotters, dedicated telephone lines going to a central control room which would plot the location of enemy aircraft on a continually updated map, and orders would then go out to fighter units to scramble and attempt to intercept them. But still, if your warning had to come from observers on the ground, it meant enemy aircraft were already over Britain by the time you first got word of them.
The original Observer Corps was Britain's eyes, but it could see only as far as the horizon. So in the 20s, they added ears.
What we've got here, what we're looking at, is an early warning detection system using acoustic methods to pick up the sound of aircraft engines. An operator sat in that little chamber, which was underground then, nice and silenced, and he listened to the point of loudest focus. When he found that place, of course, he could read off the bearings from which the sounds are coming on his equipment. Then they were passed to a central control room.
The system was somewhat effective. On a quiet night, airplane engines could be heard up to 20 miles away.
Plans exist for a chain of these mirrors all around the southeast coast of England. They were going to have one of these big mirrors about every 25 miles, and then in the gaps between, one of the round mirrors.
This expansion made sense in the 20s when planes flew slow enough to make the 20-mile range effective. But by the 1930s, they were reaching speeds of over 300 miles an hour. That meant the warning was only 10 minutes, not enough time to scramble a counterattack. The British needed something better, and in their desperation, they turned to a research scientist who wasn't concerned with enemy aircraft. He was looking for thunderstorms. His name was Robert Watson Watt.
Watson Watt's expertise was reflecting short-wave radio signals off the ionosphere to measure its height and its depth and its consistency. And one of the things that scientists working in this field had discovered was that every time an aircraft flew over, there tended to be interference.
To test the phenomenon, Watson Watt borrowed an RAF bomber and set up a flight experiment near a working BBC radio transmitter. It was a test that would change the course of history. At Cranfield University in southern England, radar systems expert Clive Alabaster can replicate the results on a smaller scale in his lab. He places a radio transmitter at one end and a receiver at the other. Above them, he hangs a metal aircraft, poised to interfere with the signal as soon as the transmitter is turned on.
There it is. And if I now pull on this string, it's going to move the airplane across the distance between the two antennas. And we can see considerable variation there. At this point, we've got the situation where the signal has gone weak. And now it's considerably stronger. And if I keep pulling, we should see this undulation continue. That loudening and quietening of the signal, that was the presence of the aircraft. That was the key to radar. It meant that radar could indeed detect overflying aircraft.
That simple demonstration sold the concept of radar to the British government. They immediately set out to turn it into an early detection system for enemy aircraft. But they were not the only ones working on the technology.
Radar is not a British invention. Radar was, in fact, invented in 8 different countries during the 1930s, but because in each of these countries it was a military secret, no one knew that the other country was working on radar.
But at that time, Britain had the greatest need for the technology, so they rushed it into service as the final piece of their interlocking air defense system. It was up and running by 1940, ready for Hitler's aerial assault. The German Luftwaffe was in for a surprise as it set out to conquer England from the sky.
The German scientists and engineers, they assumed more or less that they must be ahead of the British when it came to radar technology. But in fact, their radar technology was being used in a much more primitive way for air defense. They misunderstood the nature of the carefully controlled network which the British had set up.
Britain's defense system was codenamed Chain Home. It was comprised of a string of radar stations equipped with overlapping transmitters. Each transmitter had a receiver that could detect aircraft up to 200 miles away. From the radar stations, operators were connected by landlines to a filter room, where information was funneled into central operations.
The fundamental root of this air defense system was the rapid gathering, analysis, and dissemination of information, which then would allow you to direct fighters scrambled from the ground within 15 minutes of initial detection. And this was the miracle that took place from 1935 right to the beginning of the Battle of Britain.
There was no official start to the Battle of Britain, but when Hitler's Luftwaffe struck out across the Channel in August 1940, the British control and command system was ready. Chain Home was about to be put to the test.
We'd only been used to dealing with about 12 aircraft at a time the most. And you got this great big mass on your screen. We had to guess how many there were there.
The Royal Air Force could see the Germans when they were coming. They could keep their planes on the ground, not waste fuel, and then they could be directed to exactly where they needed to be.
The German fighters, on the other hand, were forced to engage over enemy territory, often at the limit of their fuel reserves. Facing heavy losses, the Luftwaffe made it a priority to take out the British early warning system. The Nazi bombers targeted the radar installations.
We were dive bombed August the 18th, or I could hear them coming. And then they started diving, and when they dived, they shriek, those dive bombers, a hideous sound, which is to frighten people anyway before they drop their bombs.
But even when the Luftwaffe destroyed a station, the British had backup portable units that they immediately brought in as replacements.
After we were bombed, we couldn't operate. We then went into the woods at a mobile set. A large caravan with the receiver in, and the other caravan with the transmitter. And if we hadn't got those, there'd have been a great gap. So they didn't put us out of action.
That was the strength of the chain home system. The Germans couldn't knock it out. So on September 7th, 1940, Hitler changed tactics and focused his strikes on London itself. The British stood virtually alone against the German assault. But ironically, the very technology that was protecting them would soon play an ugly role in bringing America to their aid. In those early days of the war, Britain offered many military and scientific secrets to the United States, hoping for her support in return. Radar was one of the technologies transferred, and it was quickly installed in outposts like Hawaii.
When this device was sent out to Pearl Harbor, no one really knew what to do with it. No one really trusted this newfangled device. No one knew what it was because it was a secret device, so no one had been fully briefed. And the men that were running the radar station were very junior personnel.
On the morning of December 7th, 1941, the Oahu unit located north of Pearl Harbor was manned by two volunteers, Privates Lockhart and Elliott.
And all of a sudden he sees this big wave on that oscilloscope. He doesn't know what it is. So Elliott picks up the phone. They get into the information center. And Elliott tells them, we've got this big pulse. We think there are planes coming in here.
And the man in the control room who didn't understand radar, didn't trust it, simply assumed that these guys had once again gotten their bearings wrong and had picked up a formation of B-17s that was due in that morning from California.
The technology had worked, but the system had not been set up to utilize it correctly. It was a mistake the U.S. would not make again.
Immediately, the light went off, and the Army and the Navy embraced radar with a vengeance.
The Japanese attack on Pearl Harbor drew America, with all her might and resources, into the conflict. The world was now at war on a scale never before imagined. As the Allies joined forces against common enemies in Europe and the Pacific, one weapon topped their wish list. A weapon that could carry the fight to the enemy, inflict heavy damage, and return. They needed a strategic bomber, and the technology now existed to create one. Stronger airframes with improved aerodynamics meant warplanes could carry previously impossible loads. Radio communications meant bombers could operate in fleets, forming great armadas in the sky. And improved aiming devices meant they actually had a chance of hitting their targets. The first daylight strategic bomber to enter the fray was the U.S. Army's B-17, the Flying Fortress.
You didn't have to know anything about airplanes to have the wow factor. 4 engines, could fly at a ceiling of 38,000 feet, 300 miles per hour, multi-thousand-mile range. It symbolized this whole idea of air power.
The B-17 was flown by both the U.S. Army Air Force and the RAF. It was a massive, complex machine with a crew of 10 men. In addition to the pilots, there was a flight engineer, navigator, bombardier, radio operator, and 4 gunners. Each plane was just one small part of a much larger system. 18 to 21 bombers formed an aerial combat box, which, when combined with 2 other boxes, formed a combat wing of up to 63 planes. The formations were designed to provide the greatest overall coverage against enemy fire.
The B-17 Flying Fortress bristles literally with anywhere from 10 to 12 to 13 50 caliber machine guns. And the notion is that by flying in formation, close formation, and in step-ups of boxes, you can protect yourself against enemy fighters.
See the chewed up dirt? That's where we're going to put the target.
When the British first saw the tiny ball turrets on the B-17s, they refused to believe anyone could survive in them. But the American gunners quickly proved that they could not only sit in the turrets for up to 12 hours at a time, they could also defend from them. The B-17s had aerial firepower, but their main purpose was bombing. At the heart of each plane was the Norden bomb sight, the key to bombing accuracy. The American philosophy was one of precision. The goal was to take out rail yards, bridges, factories, and radio facilities with perfectly targeted strikes.
American approaches to warfare have often entailed the belief that the use of technology can be a substitute for human casualties.
We always emphasized accuracy, and the accuracy drove us toward the rifle as opposed to the musket. It drove us toward rifled artillery, and it's this impulse that really drives us subsequently toward developing the Norden bomb sight.
The top-secret bomb sight was named for its inventor, Carl Norden. He had begun working on the device for the U.S. Navy in the 1920s, hoping to develop a weapon against surprise attacks from the sea. Enemy ships make small targets, so his margin for error was slim. He built an analog computer made up of gyroscopes, motors, gears, mirrors, levels, and a telescope. It could identify the exact moment to release a bomb, and would even take control of the plane as the moment drew near. Norden's invention was so valuable, bombardiers had to attend a special ceremony and take an oath of secrecy before they were allowed to set eyes on it.
The bomb sites would be escorted with an armed guard out to the airplane and covered with a shroud until takeoff, and bombardiers would have to swear they would protect this secret with their lives.
Almost 70 years later, the pledge is no longer binding. 2 veteran bombardiers can now reveal just how the bomb site did what it did.
I'm a high-altitude man, you're a low-altitude.
Bill Blair, on the left, served in the Pacific Theater in World War II.
3,000 feet.
And Jack Valenti, on the right, flew top-secret missions in Vietnam.
Well, we have to turn on these switches here.
Between them, they spanned the 25 years that the Norden bomb site saw service.
And we're going to select a target, like, for instance, that dam out there.
The gyroscopes at the heart of the device are the key to its success. They guarantee that no matter how much jostling the plane is subjected to, the bomb site will remain on target.
And you notice that the bomb sight stays looking the same direction, regardless of what, let me exaggerate it here.
Not only would the bomb sight give a true indication of where the ground was in relation to the horizontal, but also you could dial in the plane's airspeed and altitude and the type of bomb, and it would do a lot of the complex bomb sighting calculations automatically.
This index represents the dropping angle, and this is the sighting angle. When this coincides with this, when it bombs away, it trips a little switch in here. Okay, it's coming together, and you should hear the bombardier's voice now.
Bombardier to pilot, bombed away. Bombardier to wake center. Watch for that bomb.
A demonstration on the ground is one thing, but to test just how effective it could be, they need to take it to the air in a real bomber with actual ordnance.
Now they're ready to take real bombs aloft for an actual test.
Since the bomb sight is connected to the autopilot and actually takes control of the plane as it approaches the target, the bombardiers need to make sure they plug in the right readings.
So we'll be dropping at 3,000 feet at 150 knots, so our setting would be 43 mils.
Their readings must be accurate, because this is California, not the war-torn Pacific or Vietnam. Ordinarily, the bomber would operate above 10,000 feet, but for safety reasons, this test will take place at 3,000. Armed with practice bombs, they will attempt to hit a target less than 6 yards across.
And we found a couple pieces of steel we put as a cross right in the middle. Our bombardiers have asked us exactly which part of that cross that we would like them to hit. So there's a pretty healthy bet riding on this.
The crew takes off from an unused airstrip.
We're gonna climb out straight ahead, climb up to 3,000 feet. If you guys have a problem with the run, turn those rack switches off and call it dry run. I don't want to accidentally drop a bomb long or short, okay? Who's going first? Okay, Bill's going first. No pressure.
Ground, B-25 calling, this will be a hot run, this will be a hot run.
As they approach the target, Bill hovers over the bomb site.
Eagle Field, traffic B-25, we're overhead 3,000 feet high, Eagle Field. Okay, bombardiers, we are stable now on the bomb run. Doors coming open. Bomb doors are open. How's it going, guys? Any corrections?
Bill is struggling with the bomb sight.
Talk to me, guys. How's it going up there?
He's a little rusty after 60 years.
Is this a dry run, abort, or what's going on?
No, here, let's get this gate.
Okay, we dropped the bomb.
We dropped the bomb?
Evidently, we dropped the bomb.
What?
Okay, guys, you're gonna need to cage the gyro so we can make our turn.
Okay, gyro's cage.
Okay, start your left turn. Hey, guys on the ground, did you see that bomb go and where it hit? No, we did not see impact.
Time for another attempt.
Okay, bombardiers, we are steady on the run. How many doors coming open? Rack switch is on.
What?
Rack switch is on.
I can't do it.
Okay. Okay, guys, what's going on? We're burning up fuel like crazy here. We got to do something. What's going on? I need to know what the problem is.
All right.
Close the doors, please.
Let's let the other bombardier try for a minute.
All right.
Okay.
All right, we're having trouble keeping this doggone gyro balanced. Are you sure that the precession knobs are back out and they're not rubbing? Yes, they're backed out.
With Jack at the controls, they decide to give it another shot.
Eagle Field traffic B-25, we're rolling level on the hot run, runway 30 Eagle Field.
Okay, you wings level?
I'm wings level.
Clutch is in. Gyro's engaged. Okay, my trigger is armed.
Okay, bomb doors are coming open. Bomb doors coming open.
Okay, couple more degrees to left.
Left, got it. Got it.
Okay, you got that one. Straight up half, you're on course.
This time, Jack has the target lined up perfectly.
You got dropped away early.
They say they got a real good shot that time when they say if one more and they'd be satisfied.
Okay, you want to do a multiple drop this last time then? It's okay with me.
The crew will make one more pass, releasing all the remaining bombs as they go.
Gyros engaged.
All switches armed.
Okay, your heading's looking good.
Trigger armed. Rack switches armed.
Okay, my trigger is armed.
Bomb doors open, please. Bomb doors coming open.
A little bit to the left, just a little bit to the left. Okay, getting ready. Off the way.
Down go the bombs, sped to their target by the finest bomb sight in the world.
All three came out. Yes, thank you.
Oh, look at that! Is that classic or what? That's awesome. Oh my gosh. That is cool. That is so cool.
20 to 25 yards to the right of the target.
Yeah, it is.
Despite the difficulties, the veterans did well with the old Norden bomb site. 80-year-old Bill Blair got within 100 yards of the cross. And Jack Valenti did even better. He landed one bomb close enough that, had it been live, it would have completely destroyed the target.
Right down the middle of the road.
Real impressed.
Dang, that is something else. Good job, Bill and Jack.
Back in World War II, the Norden bomb site was the best they had. But the British Bomber Command chose a different tack, opting for heavy volume instead of pinpoint accuracy. They chose to carpet bomb the enemy, dropping massive barrages of incendiaries and high explosives onto German towns. They carried out their raids at night using Lancaster heavy bombers. The goal? To overwhelm the enemy's defenses with sustained and relentless onslaughts. The U.S. used precision by day. The RAF employed quantity by night.
The objective was to put 30 bombers a minute over the target, so the defenses were swamped by this concentration.
Such ambition required an unprecedented number of bombers.
The bombers flew in a main force stream, which usually was 4,000 feet deep in height. And if there were 1,000 bombers in the raid, the length of the bomber stream could be as long as 100 miles.
But for these armadas to be effective at night, they needed a target finder, a sturdy, fast plane that could see in the dark and guide them to their bomb drops with illuminated flares. A unique marriage of radio navigation technology, low-tech materials, and genius design would prove to be the answer. It was called the Oboe Mosquito. The Mosquito literally flew in the face of convention. It was unlike any other plane of World War II. At a time when raw materials, manpower, and skilled mechanics were almost impossible to come by, designers at the de Havilland Aircraft Company came up with the idea of building the fastest fighter bomber in the world using furniture makers, women, and wood.
They had the skills, they had the tools, and the craftsmen who could work with wood. And hence, this beautiful piece of machinery, which is actually the fastest aircraft from about 1941 to 44. Quite a feat. Timber, plywood, balsa wood.
The fuselage was built in two parts using alternating layers of thin plywood, glued together around a concrete core. Once dry, the two halves were fitted with hydraulics and other fixtures, then glued and bolted together, and united with a single wooden wing assembly and a tail fin. Construction was simple and efficient.
And that's the thickness. That's you inside there, 400 odd miles an hour on the outside. All that's separating a piece of plywood and balsa wood.
But the wooden design was stronger than it looked. The single laminated wing was sturdy enough to hold two massive 1,600 horsepower Rolls-Royce engines, making the Mosquito the fastest, most fuel-efficient plane in its class. This was a plane fast enough to evade German fighters and robust enough to carry a heavy payload of bombs and flares. But it still needed a means of navigating to its target. For this, the RAF first looked to a system used by the heavy bombers, a system known as G.
The G set was perhaps the navigator's most important aid.
G worked off a chart that corresponded to a series of UK-based radio signals.
What we're trying to do is measure the time difference between the arrival of two pulses transmitted from two stations in the UK. There's one located at the focus of this hyperbola, there's another one at the focus of this hyperbola. You receive the signals exactly at the same time. You will be on a line that intercepts the two stations. If you receive the signals at a later time or an earlier time, then you'll be on another line that is either this or this side of the transmitter. Using two sets of lines, where those lines intercept, that will be your position.
The G system gave bomber crews a useful navigation tool, but its accuracy diminished over distance, so it was almost useless for targets far from the coastline.
When you went over to the French coast, the accuracy might drop to 1 mile. Nearer to Germany would perhaps fall to 2 miles. And when you got deeper into Germany, you might get a fix with an accuracy of 5 miles if you were lucky.
G was effective for general navigation by the vast fleets of British planes, but the Mosquitoes needed something far more accurate if they were to lead the armadas to their targets. So the RAF tried a system that dedicated two separated radar stations to a single aircraft. One station was for tracking, the other for bomb release. By following the signal from the tracking station, the plane would fly towards the predetermined target. When it intersected the signal from the release station, the pilot knew he was over the target and the colored flares were released. Codenamed Oboe, for the sound the two signals made when they met, the system proved ideal for the Mosquito's role as a pathfinder.
Oboe could control one aircraft to locate a target. It was so precise that the Germans thought that they had somebody sitting on the ground with a radio transmitter directing the aircraft in. You could almost hit you could hit an individual factory.
With the Mosquitoes guiding the way and marking targets with different colored flares, the huge Allied armadas began to turn the tide of the war in Europe.
The markers had been dropped by Oboe Mosquitoes, who were the most accurate, and the master bomber would broadcast to the main force, bomb the center of the Reds, or bomb just to the starboard of the Greens, and so on.
Blind bombing, as it was called, was learning to see quite well.
By late 43, early 44, Bomber Command could bomb more accurately by night than the U.S. Army Air Force could by day because of Oboe and G.
Effective bombing at night had become a reality in Europe because the bombers were part of an integrated system. Interlocking technologies were providing the key to air power. The war America was fighting in the Pacific required even more collaboration. Here, the synchronization of air, sea, and land forces was the only option for defeating an enemy spread out over such vast expanses of open ocean. Japan was so far away, it could only be hit from the air. But such long-range attacks required copious resources: bases, airstrips, ammunition, and fuel supplies. They also needed planes that were powerful and fuel efficient enough to cover the huge distances. The B-17s were proving effective in Europe, but here something bigger and better was needed. The answer was the Boeing B-29 Superfortress.
The B-29 was almost twice the B-17 any way you cared to measure it. It had about twice the payload, twice the horsepower of the engines, twice the range. It was one of these technological milestones that so perfectly represented what it was.
In a giant hangar at Boeing's Wichita, Kansas facility, a small army of veterans is rebuilding a B-29 that left for war from this very site over half a century ago. When the war ended for Doc, a short retirement was followed by a longer stint doing target practice in the Mojave Desert. Doc was the target. Somehow he survived and is now back in safe hands.
It actually has come home to be reborn. You take a look at this structure. It's a massive airplane, 99 feet long, 141 feet 9 inches wide. Grossed out, it's just a monster.
Here we go.
Aerodynamically, the B-29 was the most advanced warplane of its day. Even the rivets were polished flat to eliminate drag. The fuselage was a bullet-nose cylinder that housed a complex web of the latest electronics and avionics.
We were dealing here with a number of technologies that had to come together and with a mass industrial effort that had to be assembled and built to get this aircraft in service. It was an all-metal airplane. It was highly streamed to an unprecedented degree. Indeed, when the landing gear was retracted into the airplane, it cut the drag of the airplane fully by half, indicating how highly refined the design of this airplane was.
The B-29 flew further, faster, and higher because it had to. It had been designed for a very specific task. In 1944, the only way U.S. bombers could reach Japan was via improvised airstrips on mainland China. They, in turn, could only be approached via bases in India. That meant crossing back and forth over the high Himalayas. That was the B-29's run. And since the air at the roof of the world was thin and cold, the B-29 would be the first pressurized warplane. The pressurized sections were heated and connected by a system of tunnels. For the first time in almost 40 years of military aviation, the crews could come in from the cold.
The gunner could sit here in his in shorts if he wanted to, and they actually did that, and in a t-shirt, and pressurized, and in comfort. And he could sit here and then work the gun sight away from the guns, and that made the gunner, he was a lot sharper as a result, and he could do his job a whole lot better and for longer periods of time.
The centralized controls inside the warm, comfortable plane were popular with the air crews, but the pressurized compartments brought benefits and new risks.
Being pressurized would be just like this at over 30,000, you know what I mean? But actually we were not supposed to be pressurized over the target because your deep compression was so quick that your gases would rupture your stomach. But being young bucks, we flew all of our missions, high altitude missions, pressurized.
This attitude stemmed from their confidence in their warplane. Early computers and lightweight electronics, combined with built-in life support and internal communication systems, meant the Superfortress was uniquely self-sufficient.
With the B-29, we see the blending of the emergent electronic revolution with the traditional aeronautics revolution. And this will lead us to what we term eventually weapons systems, aircraft that have a very strong electronic component to their design.
On June 5, 1944, the B-29s flew their first combat mission. Armed with Norden bomb sights, they were at last within striking distance of Japan. But the high-altitude planes ran into an unexpected problem.
The jet stream over the Pacific was so strong that if you came into the jet stream over a Japanese target, you were practically standing still. And if you flew over the target with the jet stream, you were jetting across so that you just couldn't hit anything.
At 30,000 feet, the B-29s could reach Japan, they just couldn't hit it. In July 1944, Bomber Command was handed over to General Curtis LeMay. Fresh from the European campaign, LeMay switched to a more familiar strategy.
Curtis LeMay says, to hell with all this foolishness. Take the defensive armament out of the B-29 except for the tail turret. Get rid of all the pressurized systems. We're going over Japan at low level, at night, with incendiaries, and we're going to burn those cities to the ground.
The shift in strategy worked, and the stripped down but heavily loaded B-29s became a devastating weapon.
At the lower altitudes, they would hang as many firebombs as they could on the racks, and then they laid them up in there even. And when the bomb bay doors come closed, there was just about that much room.
As island after island fell to U.S. forces, the bombers closed the net on Japan. Desperate to end the war, LeMay had no qualms about rejecting the American philosophy of precision bombing in favor of the low-level carpet bombing approach of the British. On one night alone, 853 B-29s bombed Japanese cities.
For all its emphasis on pinpoint bombing, strategic bombing, and the use of the northern bomb site, the American Air Force resorts to area bombing, or what is sometimes called terror bombing.
But despite the endless barrage, the Japanese refused to surrender. So the U.S. advanced another plan, one that would change the rules of war forever. On the morning of August 6, 1945, the B-29 was given a new mission, one that it alone could fulfill. The world's biggest bomber would carry the world's first nuclear bomb.
The B-29 program was more complex and more technically demanding than even developing the atomic bomb.
We talk about systems. The atomic bomb wouldn't have been anything without the B-29.
Aviation in World War II had been about radar and bombers. It ended with the bomb. What began with the arrival of air power was now foreshadowing the threat of total air supremacy. By 1945, the world's leading nations all had air forces. Planes with integrated systems flying in integrated formations. Radar was rapidly becoming a worldwide network. And because of aviation, the global combat arena was shrinking. At Hiroshima, a single plane delivered one terrifying message. No place on Earth was safe from the warplane.
For more information about the 100 years of military aviation history, please visit pbs.org. A multimedia timeline will reveal how warplane technology has transformed the way countries wage war. Warplane is available on DVD for $24.99 plus shipping. To order, call 1-800-336-1917 or write to the address on your screen.